In chapter 1.2, we will study the equivalent distribution of the electrons and the holes. Follow the last lecture in chapter 1.2, we will apply the concept of density of state and the Fermi-Dirac distribution of the electrons to calculate the amount of the carrier concentration in each energy level. First of all, we should explain what is the thermal equivalent situation. That means that the thermal temperature is constant without any change as time goes by, and there is no external force, including the voltage, electric field, magnetic fields, or any change in the temperatures. So when we try to plot the density of state and the Fermi distribution, you can see that we already know that the density of state in the conduction band is proportional to the root of energy. So the curve looks like this. And in the Fermi-Dirac distribution, it is the E plus exponentials under 1. So that plot can be plotted in this way. So when we want to confirm the electron concentration in the conduction band, we can times the density of state and the Fermi-Dirac distribution in each energy. So that's the reason why this carrier concentration looks like this shape. And the total electrons in the conduction band can be obtained by integrating all this amount of the carrier concentration as shown in this equation. In the whole carrier concentration, that will be opposite. We will integrate the energy from the valence band edge to the bottom of the energy, which is you can see it's assume it as a minus infinite position energy. And the distribution of the whole will become 1 minus Fermi-Dirac distribution. That is the opposite to the electron Fermi-Dirac distribution. So let's quick review again. So we are interested about this region. To understand, there are a lot of states that the electron can be occupied, but the probability that the electron can occupy in each energy level is shown in this blue curve. And for holes, that is the opposite. So we should look at the 1 minus Fermi level, which means the area of this region. And for electron, we will look at the area of this region. That is the opposite region. So based on these figures, we can calculate by this formula with a more accurate number from the integral of density of state and Fermi distribution. This is the formula that we get from chapter 1.1, and this is also based on the Fermi-Dirac distribution, and this one can be approximated by as a Maxwell-Boltzmann approximation, but that will be applied later. Let's use the original Fermi-Dirac distribution first. After arrange the equations, finally we can get the carrier concentration that is valid in all situations. However, the issue is this we call it as a Fermi-Dirac integral of order half. This eta f is this cannot be solved by using in this equation. We need to use a numerical way to estimate the amount at each energy level. So based on this concept, we can apply the Boltzmann approximation to understand when we can simplify this this Fermi-Dirac integral. You can see that if the energy and the x-axis is the distance between the Fermi level and the conduction band. If the Fermi level is far from is below the conduction band more, it means the value will become more negative. So if the Fermi level is not is far from conduction band, means that uh, the doping carrier concentration is not too high. You can understand it's a lightly doped. And why when the Fermi level is lower than far from conduction band means lightly doped, we will explain later. In that case, if it is not a extremely highly doped situation, then you can say that the distribution or the Fermi-Dirac integral value is similar between the Boltzmann-Maxwell distribution and the Fermi-Dirac distribution. And in that case, we can simplify the Fermi-Dirac integral to the Maxwell-Boltzmann approximation, which is valid around E minus EF around the distance between conduction band and the Fermi level is larger than 3 kT. So this is the number as I mentioned. So if the n eta f means the distance between the Fermi level and conduction band is larger than 3 kT, then these numbers the red part, these numbers are almost the same. But if it is close to the conduction band, then these two models will have the different values. So the first column is the Fermi-Dirac distribution that is valid in any situation, and this is an approximation that is dependent on the exponential eta f. So the conclusion is that if we want to simplify the Fermi-Dirac to Maxwell-Boltzmann approximation, then the EF and the EC should be larger than 3 kT. The difference between them should be larger than 3 kT. And this Fermi-Dirac integral can have many numerical answers. If you need to solve them, then we will give you the table to understand what is the value of it. Okay, so let's go back to the original formula. If we can use the approximation, Boltzmann approximation, when EF and EC the distance is larger than 3 kT, then this formula can be simplified and arranged in this way. Then finally, this is the total carrier concentration. And this part in front of the exponential is a constant. We call it the effective density of state of conduction band. And this part is the dependent of the energy with the Fermi level conduction band and difference will determine what is the carrier concentration of the electrons. So we can simplify it as carrier concentration equals to the effective density of state of conduction band times the exponential minus EC minus EF over KT. And this constant is, as I mentioned, is the effective density of state that is mainly determined by the effective mass, which is density of state effective mass, not the conductivity effective mass. And it is dependent to the temperature 3 over 2 power of law. So it is not the same, but if we assume effective mass density of states effective mass is equals to the rest mass, just simplify and use the temperature as the room temperature, then the value is around 2.5 times 10 to 19 centimeters minus 3 centimeter to minus 3. For whole carrier concentration is similar as electron, just use the formula with the right density of state in the valence band and the distribution, Fermi-Dirac distribution in the valence band. Then we can also simplify it by Boltzmann approximation when the distance between Fermi level and the valence band H is larger than 3 kT. And we can also get the effective density of state in valence band. and this value is also around 10 to 19. So a summary, the table summarizes the density of state of conduction band and the valence band in different semiconductor. The value is high to around 7 to 10 to 17 to 10 to 19. And for the effective mass, as I mentioned, generally the effective mass should be lower than the rest mass of electrons. So you can see here. And if the effective, for example, for germanium, the effective mass is lower than silicon, it has a higher mobility, but it also have a relative lower density of state, effective density of state of conduction band and valence band. So there is a good for mobility, but also lower density of state issue. So there is a trade-off you need to think about it. Next, we can understand the position of conduction band, valence band, and Fermi level, and we want to interest you another concept in the band diagram is the intrinsic carrier concentration. For intrinsic carrier concentration, it means that there's no impurity atoms or lattice defects. It means that the whole carrier concentration and the electron carrier concentration are the same. And the other important concept is that the hole and the electron pair, actually it is not no hole or no electron. That is, it means that the hole and the electron becomes a pair. They will generate simultaneously by thermal excitation across the band gap. It means that the amount of hole formed, and then that value will be the same as the amount of electron formed. Then we can try to, so that's why the electron carrier concentration should be the same as the intrinsic carrier concentration when it is an intrinsic semiconductor, so as the whole carrier concentration. And their carrier concentration is determined, expressed by the distance between the Fermi level for the intrinsic Fermi level and the conduction band. And for hole is the intrinsic Fermi level and the valence band. So there is we need to know where is the position of the Fermi level, intrinsic Fermi level. That will determine the carrier concentration of the intrinsic semiconductor. And since these two values are the same, so when we try to times them together, and it will disappear after they times together. So you can simplify us here, as shown here. The intrinsic carrier concentration is independent of the intrinsic Fermi level. It is only dependent on density of state of conduction band and the valence band, and the band diagram, and also the temperature. So give an example, what is the value of the intrinsic carrier concentration for silicon? If we use the room temperature and the band gap is 1.12 electron volt, and the value is 6.95 times 10 to 9 centimeter to minus 3. Actually, this is the value using the above equation, which is a bit lower than the value we commonly use in your previous learning in electronics lecture. And why there is a bit different, slightly different, the reason is that this value is maybe this value we commonly accept, that is using experiment to determine it, which is electron synchrotron wave, and that is also time dependent because it measures at a very low temperature, so it's more accurate in the real experiment. And the other thing is because above equation is using the assumption of the 3D finite equipotential well, so there something is simplified. So that's why there is a bit slightly different. but actually it's already quite close, only 2 times different. That is quite close. Yeah. Next, so we can use the above equation shown here, which is independent of the intrinsic Fermi level. We just need to know what is the band gap, because why? The physics you can see that if we plot the band diagram here, and this electron hole pair will form, and this generation rate is determined by the I would say this electron hole pair how the probability they form is determined by the distance of the band gap. So that's why band gap is important. And also the temperature is also important, because this is a thermal process. And how many states that can be formed is also determined by the density of state of the effective mass. So you can see that for example, again, for silicon and germanium, the germanium band gap is smaller. That's why the intrinsic carrier concentration is also higher. So you can plot it if under the same temperature, germanium has a higher concentration than the intrinsic carrier concentration than the silicon. And the gallium arsenide has an even larger band gap. That's why it is even lower. Okay, so the next question is the intrinsic Fermi level's position is located in the mid gap? The answer is no. It is close, but slightly different. If we use the formula as I mentioned in the previous slide, then this is then we try to let's see, we try to say that okay, they are the same, and we want to know what is the value of we use the intrinsic carrier concentration of hole and the electron separately, and that should be the same for intrinsic semiconductor, and then we can derive the intrinsic Fermi level shown here, and the conclusion is that the mid gap and the intrinsic Fermi level has a slightly different, determined by 3/4 kT natural log exponential log of effective mass of hole over effective mass of electrons. So they can be different only when the effective mass of hole or electron are the same. And this value will be 0. But generally, most of the semiconductor has a different effective mass between hole and electron. And this value actually is not large, but yes, but there are still a difference there. So you have to understand that they are close, but not the same. And that is determined by the effective mass difference between hole and electrons. Okay, and after explaining the intrinsic semiconductor, let's move forward to the extrinsic semiconductor, which is, we can also say it is a doped semiconductor. So how the intrinsic semiconductor can be doped? That's always start from silicon again. Silicon is a four group semiconductor. So there are many 10 to 20 of the atoms in this solid. The concentration is like that. So once if we try to pick up some of the proportion to replace the silicon as a fifth group, such as phosphor as a donor, then generally the electrons has 4 for silicon, but for phosphor they has one more electrons compared more than the silicon, and this silicon will makes this whole solid still as a neutral situation, which means that in ideally it is not ionized situation. But this fifth electron will start to has the like a movement as a circle motions, and this motion is has a center force which is formed by the Coulomb force. And the next part is when this electron has a circle movement around the phosphor. These 5 electrons, what is the distance between the phosphorus and this fixed electron compared to the distance of the silicon and silicon atoms? Since it is additional electrons movement in this periodic silicon lattice, that's why we can make the semiconductor becomes n-type with the donor concept. In opposite, if we replace the silicon by the third group atom, such as a boron, then there will become like a empty state of the electrons layer, which will attract the electron to field, and then the empty position will change. So you can regard it as the additional hole it has a movement surrounding the phosphor, which is also like a Coulomb force with a certain distance. And since this model, it means that there's a vacancy of the electrons, so we can say it is kind of the acceptable concept. Okay, then let's further understand what is the physics behind these electrons. If the semiconductor is doped, we were interested about what is the donor state, energy position, and what is the amount, how it can be ionized once this 5th electron is the bond between phosphor and the 5th electron is broken. Then that electrons can becomes a free electron doped in the semiconductor inside the conduction band, and the location of the phosphor will becomes like fixed positive ions. So we need to understand when it will has that concept that makes this 5th electron be broken. The bond between them will be broken, and I can offer the donor impurity. For acceptor, it's opposite, like because there is an empty state for electron to field. So you can understand is the hole in the valence band when they can try to form once the acceptor level is provided from the ionized boron. Because the why the arrow plot like this means that the electrons, fully filled electron, can fill inside this ionized boron, then it will create more empty state in the valence band, which means that we can consider it as a hole. So again, so as I mentioned above, the reason why we plot the donor state or acceptor state energy level as a discrete way is because there's no interaction between the atoms of the phosphor or boron, and actually the number of the donor or acceptor atoms is much less than the number of the silicon atoms, and the 5th electrons of the phosphor actually is limited. It's a locally donor state, donor impurity, not it didn't change the total band structure of the silicon, and it is independent of each phosphor. If that's the situation we assume, and once the boron or phosphor is ionized, those ionized states actually is fixed, which means that it will not contribute the conductivity in valence band or conduction band. So we just need to focus on how many donors or acceptors can be formed by the impurities, and that is determined by the donor level or acceptor level. Okay, so since there is a circle motions, and we can use a simpler way to understand it from the Bohr radius and the Bohr ionized energy. So we know the radius of the donor orbital have this Coulomb force of attraction, and this centripetal force of the orbiting is equals to the effective mass. No, actually, it's not. It should be the it should be the the effective mass times the velocity square over the radius at each principal number. And the quantized momentum can be expressed in this equation. Therefore, the radius can be this of the donor orbitals can be shown here. Since it is a bit complicated formula, and we just need to understand, we can express it in a simplified way by comparing it to the Bohr radius, which is the value is shown here, and the number we know is around 0.53 angstrom. Before going to the get the value, I want to emphasize that why we only use z equals to 1, not the number of the charge, total charge of the or total electrons in the phosphor. It is because we assume that there is only the fifth electrons is additionally move as a centripetal motions. Not total electron is ionized. So only one electron is moving in the silicon crystal. So this is not a different concept as the Frostov atoms model. This is just the fifth electron's centripetal motions. So that's why z is only equals to 1. Then, if we try to get the ratio between the radius we want to know compared to the Bohr's radius, then we can know that the ratio is around determined by this formula. And if we put the silicon's value inside this formula, and the ratio is around 55 times larger than the Bohr radius, which is around 23.9 angstrom. And this value is around 4 times larger than the lattice of silicon. For the binding energy, we can do the similar things, so I don't need to go through the details. So we know this is the binding energy in the Bohr model, the hydrogen model. Then we can get the value of the binding energy for phosphor. It's around 2 times larger than the binding energy in the hydrogen. Then we can when we calculate this value is 2.25 minus 25.8 millielectron volt. Actually, this distance is very small, which is almost close to the conduction band. That you can understand this binding energy. If the binding energy is smaller, that means that this loose electron is easily to lose and occupy inside the conduction band, provide the donor. So the smaller the binding energy is, the easier the loose electron can occupy in the conduction band. These graphs summarize each donor's ionized energy as the impurity in silicon for conduction band, and also as a donor, and the valence band as a receptor. So when we look at the table, if we want to dope the silicon easily as a donor, then we can use phosphor, antimony, or even Li as the donor. and that is called when the different distance between conduction band and the binding energy is less than 1 kT, then we will say it is a shallow impurity. But if it is deeper, then we will say it's a deep impurity. And generally, for the ionized binding energy in silicon, electron is smaller than hole. It is because the effective mass of electron is lower than hole generally. So for silicon, it is. So that's why it is more easily to dot the provide the donor in the conduction band than hole. As you see, that is determined by the effective mass of the electron or hole. Because electron effective mass of electron is lower, so this value is also lower. Hole is a bit higher. Okay, so based on the understanding that the extrinsic semiconductor, then we can try to extract the extrinsic carrier concentration move from this concept. In the thermal equivalent concentration, holes and we assume that the electron in holes is non-degenerate semiconductor. The non-degenerate semiconductor means that it is intrinsic carrier concentration semiconductor, but the doping level is not too high. And how to define whether it is too high? It is determining on what is the, we can understand if the EC and EF is larger than 3 kT. Even the EF is high, is increased, but not still far from EC. Then we can say it is a non-degenerate semiconductor. Then the formula can be almost the same as the intrinsic carrier concentration of electron in the hole. We just change the intrinsic Fermi level to Fermi level. And that is the same for hole carrier concentration. So in the future, when you see the Fermi level is shifting from intrinsic position, which is close to the mid-gap, gradually close to the conduction band, that means that the electron carrier concentration becomes larger. And also, as well as the hole, if the Fermi level moves forward to the valence band, that means that the hole carrier concentration is increasing. If you want to understand it as using the graph, you can see that, as I mentioned, the density of state in the conduction band is fixed. We just change the probability when the electrons can be filled inside the density of state. So if we look at the edge of the conduction band, when Fermi level moves forward to the closer to the conduction band, the probability for electron to fill at the lowest minimum point of the conduction band increase, and that's why the total carrier concentration from EC to far from the EC in the conduction band increase in the O region. In the opposite, for hole carrier concentrations, probability reduce. So that's the way you can understand why the electron carrier concentration becomes higher when Fermi level is closer to the conduction band by using this graph. Next, we understand that the formula is shown here. So if we want to rewrite it from not only using EC and EF, we want to use it as the intrinsic carrier concentration and intrinsic Fermi level. Then we just change the parameter here, include the plus intrinsic Fermi level and the minus intrinsic Fermi level. And you can become this another way to express the hole and the electron carrier concentration by using intrinsic carrier concentration and the intrinsic Fermi level. I will not go through the details, so you can understand that if the formula is, again, if it is close to the conduction band, far from the intrinsic Fermi level, then the whole electron carrier concentration is increasing. And if it is far from the conduction band and close to the intrinsic Fermi level. That means that electron carrier concentration becomes lower. And that is opposite and the same as the direction is the opposite, but the concept is the same for hole. Next, we want to explain the concept that is NP product or the mass action law. So when the mass action law is valid, it is valid when it is an intrinsic semiconductor or extrinsic semiconductor, but not degenerate at a given temperature. And in that case, you can understand that it's like an acid and alkylate product, like a pH value. So that is equation and equilibrium equation between the electrons and hole carrier concentration. That will be the NP product means that their product's value should be constant, determined by the intrinsic carrier concentration square, regardless of the doping, by deriving the equation. Because finally, you will see that the Fermi levels between them they can be disappear during the deviation. So the only thing left is the band gap. So as we mentioned, the intrinsic carrier concentration is only determined by the band gap. Even it is doped semiconductor, you can use it, unless it becomes the degenerate intrinsic semiconductor. Then this equation is not valid. This is because then we cannot get this formula by the Boltzmann approximation. Okay, so followed by the last sentence I said in the last slide. So when we move from the non-degenerate semiconductor to degenerate, means that the Fermi level moves forward to the conduction band. Means that is a heavily doped semiconductor. It can move even above the conduction band in some situation, like the carrier concentration is a strongly doped or some pinning issue, any other way. So the conduction, the electron is almost fully filled at this region. So in that case, the formula of the electron carrier concentration should go back to returns to the Fermi-Dirac interval function, which is a general solution for all the situation without using the Boltzmann approximation. And if we give the value and to roughly estimate the carrier concentration with a very high carrier with degenerate doped semiconductor, the value is almost close to the density of state of conduction band when EF is located at the EC. That is also the same concept for the holes, and I won't go through the details. One more concept is that once a lot of electron is occupied in the conduction band, and it can also start to have some interaction. It is not discrete donors. It becomes the continuous or some interaction between each atom because the electron concentration is too high. Then it will try to split into some energy band in this periodic potential well from the donor's potential, from the donor's contribution. And with this splitting of the energy, which will make the conduction band energy will become lower. So we call it impurity-induced band gap narrowing, because the conduction band split into more bands and becomes lower. And the other concept is we just mentioned that ideally we just mentioned the binding energy and how much probability that the electrons can the fifth electrons of the phosphor can be occupied in the conduction band. Actually, it is also the probability function for the ionization. And this probability is also similar as the Fermi-Dirac distribution. The only thing is it should follow the degeneracy factor for each semiconductor, or it depends on it is electron or holes. And this degeneracy factor for silicon and for electron of silicon, it should be 2. And the reason it's 2 is because of the Pauli exclusion principle. And for hole, the degenerate factor is around 4 for silicon and gallium arsenide due to their band structure, and we won't go through the detail here. So based on this probability function, then we can understand that this is the amount that can occupy the final amounts that can occupy in the state of a conduction band. So this ND means that there is a total electrons of the phosphor here. And why is this electron occupying the conduction band? Then you can regard this phosphor becomes ionized as a positive one as an ionized charge, fixed charge. So that is the definition of this free value. And this electrons is the main donor. So we can try to calculate the carrier concentration by using the probability function for the ionization. By deriving the formula, and finally we can, since the ionized the binding energy of the donor level is still larger than the 3 kT, we can use the maximum Boltzmann approximation. And this is the original carrier concentrations formula. So we want to understand the original carrier concentration. What is the ratio between the original carrier concentration and the ionized carrier concentrations, the amounts of them. And when we look at that, we can find out that actually the ionized electrons amount of the electron that will leave at the binding energy is quite low at the room temperature. It means that almost the electron is filled inside the conduction band, not leaving at the donor level. So we call it as a complete ionization. This is a typo. It should be the undoped silicon. And in the opposite concept of the complete ionization is a freeze out, which will happen at the 0 K. It means that for donor state, it is located, the electron will not occupy in the conduction band, not fully upon ionization. It will totally leave at the binding energy donor level. So in that case, the ND will equals to the amount of the donor concentration, and the ionized donor is going to become 0. And this ionized probability distribution of probability function for ionization, probability function for the ionization will become like this formula. So why this Fermi level will locate in the middle between the half between conduction band and donor? It is because all of the electron is filled, is freezed at the donor level. So when we look at the definition of the Fermi distribution, you can understand that this is 100%, and the conduction band is almost no carrier concentration, no electrons. So the half probably the half of the probability, 50% of the electron can be filled is the position of the Fermi level, which is in the middle between conduction band and the donor level. And that is also had for the freeze out of the hole as a similar concept, means that the Fermi level, the hole is totally remain in the acceptor level, and the Fermi level of in this freeze out situation is in between of the valence band H and the acceptor level. So you can see that actually when we reduce the temperature from room temperature to 0K, the Fermi level will shift from near intrinsic Fermi level to shift up to the close to the conduction band, which is higher than the donor level. But the carrier concentration is reducing, even though the Fermi level is moving forward. So you shouldn't be confused in this situation. You need to understand it separately. Okay, the next concept is the charge neutrality. It means that, as I mentioned, when we dope the semiconductor, no matter is a donor or acceptor, in the ideal case there is no ions. It may have an ionization process, but the total charge should be neutral. There is no positive or negative charge in the total dope or undoped semiconductor under the thermal equilibrium. So for electrons and holes, you will have thermal electrons and thermal holes. And if it is a donor, there is a donor donor in the semiconductor, then they will create the donor electrons and also the ionized phosphor here. And if we have acceptor holes, then we will have the ionized boron here. However, no matter it's a donor or acceptor, as I mentioned, all of the ideally in the thermal equilibrium, the net charge should be 0. Okay, and let's see how many positive and negative charge we have. For negative charge, we have electrons, so we can calculate the amount of total electron carrier concentration and also the negative charge of the acceptor, ionized acceptor. For the positive charge, we have a total hole carrier concentration, as you see here, and also the ionized donors. For ionized donors, you can explain by the doping carrier concentration minus the remain donor concentration at the donor level, and the same as for hole. So now for n-type or p-type, how do we determine? It depends if there is n-p-type, also donor and hole in the same semiconductor. It just depends on what is larger. If it is complete ionization, if ND is larger than NA, it will be n-type. NA is larger than ND, and that is a p-type. And if ND is equal to NA and has a fully with the complete ionization, then we will call it compensate semiconductor. And actually, the behavior is similar as intrinsic semiconductor. Okay, and because we have dopants here, so we want to understand what is the carrier concentration if we have both acceptor and the donors in the system. For electrons, source is from the thermal electron hole pairs, as I mentioned here. So we have both in electron and holes. And for another donor concentration is from the donor electrons. For hole, it is acceptor. Here is the typo, acceptor holes. Then we can get the total carrier concentration by using the we can use the charge neutrality equation to solve them. Since, for example, if we just have the donor in the system, then we don't have the value. Sorry, let me make a change in the word. Since we have acceptor, if we just have the acceptor in the system, then we don't know what is we want to sorry, we have a donor acceptor in the both system, but we want to solve N0 and the P0 individually. So since if it is not the degenerate dose semiconductor, then we can replace the P0 by Ni squared over N0 based on the max action law. And by solving this to the equation, we can get the carrier concentration of the whole. And we can also replace the N0 as N intrinsic carrier concentration squared over P0. We can also get the general solution of the whole carrier concentration. So you can see that although we said that the total amount of electrons carrier can be the thermal equivalent electron carrier concentration and also the donor concentration, but it is not directly add them together. It is an equation between this situation because of the NP product. However, if this value is much larger, for example, if the ND is much larger than NA, then this N0 is equal to ND. And if ND is NA is a more like an intrinsic situation, then N0 will equal to Ni. So if we plot the carrier concentration as a function of temperature, when the temperature is very low, close to the freeze out, then as I mentioned, the donor, no matter donor has the receptor, there is no additional electrons or hole can provide in the conduction band and valence band. So the carrier concentration will be more like an intrinsic situation, which is very low. But once it can have some temperature to activate and the loose electrons can become the donors, then it can become partially ionized. And so the carrier concentration will gradually increase. So, but it can easily increase with just a bit temperature, even it's lower than room temperature. So around 100K, it can be complete ionized. So at that time, the temperature will be almost the same. Sorry, the carrier concentration will be almost the same for this. It fully is a complete ionized extrinsic semiconductor. But if we further increase the temperature up to like 500 or 600K, it means that in the formula, this value will become intrinsic carrier concentration will become larger and gradually dominate. Once it suppresses the extrinsic carrier concentration, then this value will be dominated by intrinsic carrier concentration behavior. So that's why the carrier concentration will become like this, depend as a function of temperature will become in three regions. First part is the onset, after onset of result, partial ionization, complete ionization for extrinsic semiconductor, then the intrinsic carrier concentration will overcome. It will be much larger than the extrinsic semiconductors complete ionization concentration. So this is the redistribution of the formula with the dopants. As I mentioned, if the formula is shown here, then we know the value of the carrier concentration can be simplified as ND. If the ND is much larger than NA, then it can be a simplified way to show their relationship. So then N0 we don't need to derive the formula here. You just have to understand ND is much larger than NA, then actually normally N0 should be close to ND under complete ionization. And that is the same for P0. And we can, so if we want to know the carrier concentration of electrons, generally for complete ionization donor, it will be equal to ND, and the P0 is much smaller, but we can also extract it from the mass action law. You can express also by ND. Same as the whole, using the same concept. And for the Fermi level as a function of the carrier concentration, you should always know that you can check the carrier concentration by the position of the Fermi level. If it is higher carrier concentration electron carrier concentration, then the Fermi level will become move forward, move closer to the conduction band. If the whole carrier concentration is higher, then the Fermi level will move closer to the valence band. Since this formula is listed here as shown in the previous slide, we are interested. That's why it is exponential, natural log of NC over N0. So actually, this is almost, if it is a log scale, this is almost a linear dependent between the Fermi level and the conduction band difference as a function of the carrier concentration. The relationship is almost linear. But when it becomes not linear, it becomes like a close to saturation. Actually, the answer is when the Maxwell-Boltzmann approximation is not valid, then we can use this simplified equation to describe their Fermi level position and the carrier concentration. So it can be the interesting question is when this the maxima carrier concentration is doping carrier concentration is valid for Boltzmann approximation. So you just need to understand that. That means that the Fermi level and the valence band this difference between them should be 3 kT. And then you can derive all the equations shown here. And I won't go to the details of this example. Then you can extract what is the doping concentration, acceptor doping concentration, if it is the complete ionization. The last slide of the chapter 1.2 is Fermi level as a function of temperature. So as I mentioned, when the temperature becomes lower, it will become gradually freeze out, and that's why the Fermi level for N-type will move forward. It will be moved close to the conduction band, and even should be higher than the donor level, and the position should be at the freeze out should be a half between the conduction band and the Fermi level, and that is opposite for the for the whole p-type semiconductor. And when the carrier concentration, when the temperature goes higher, since the intrinsic property dominate, so that's why the Fermi level will move to the mid gap, or the Fermi level, intrinsic Fermi level, which is close to the intrinsic Fermi level. So that's why the 50% of the electron hole the probability is of them is close to the middle, and which is close to the mid gap of the band gap at higher temperature. So that is all for the chapter 1.2.